Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in the last session we discussed the vacuum environment of spacecrafts and we discussed what are the characteristics of the vacuum environment and how this affects the spacecraft. So, first we discussed that is the extreme temperatures. So, in the absence of the atmosphere or in a vacuum like environment, the space, the temperature, there is extreme temperature fluctuations on these spacecrafts. So, when the full sun load is there, the spacecrafts can acquire a temperature even more than 100 degrees centigrade, and whenever there is no sunlight, that is when the spacecraft is shadowed by earth or it is in the eclipse, then it can go to a temperature of even minus 100 or even below that. So, this gives a challenge to the spacecraft designer to design a effective thermal control system, because in vacuum the heat transfer also, the mechanism of heat transfer is only limited to the radiation and conduction. Then you have seen that because of the absence of the atmosphere, the satellite is exposed to the harmful radiations like UV radiation, X-rays, alpha rays, gamma rays, all these things the spacecraft is exposed. A third phenomena I have seen, that is in vacuum, and phenomena called the outgassing happens. So, today we will continue with the outgassing. We will try to understand what is the mechanism of outgassing, how the outgassing happens and how this outgassed material is transported to other bodies. So, that also we will see. So, what is the outgassing mechanism? So, outgassing depends on three processes actually. The first we will discuss, that is the diffusion. So, all of you know that the diffusion is the process whereby the atoms or the molecules move from a region of higher concentration to a region of low concentration, and this homogenization, that is a tendency to make this media homogeneous media. This occurs because of the random thermal motions of the particles. So, the contaminants that diffuse to the surface of an organic material may have enough thermal energy to escape the surface forces, okay, and then evaporate to the local environments. So, this only can happen when there is this ambient environment is a vacuum like environment, there is no pressure because of the environment. The second process is called the disruption. So, disruption is the physical process where the absorbed atoms or molecules are released from the surface into this surrounding. So, here this outgassing, it happens only from the surfaces. The third phenomena is called the decomposition. So, what is decomposition? So, decomposition is a type of chemical reaction where a complex compound, it divides into two or more simpler substances, and after that this may outgas through disruption or diffusion. Okay. So, the process of decomposition generally it contributes very little to the mass loss, because as we have seen, that is the effect of the outgassing is the mass loss of the spacecraft bodies. So, the decomposition it contributes little to this the mass loss because of the higher energy requirement. Here for the decomposition, this activation, you need more activation, higher activation energy, and generally this type of materials are also not used in the spacecraft, which can get decomposed. So, the contribution in the outgassing process by the decomposition is ruled out. The second process is disruption. Process also involve total, that is the total mass loss very little, because the process removes the material only from the surface. But in general, there will be the material which will be trapped inside, some of the material, it can be fault or some void. So, there will be material inside. So, in that case disruption also is not an effective or which we need to consider. Thus, the decomposition and the disruption contributes very little to the mass loss due to outgassing. So, the diffusion mechanism is the only mechanism which is responsible for the outgassing from organic materials, and since diffusion involves the total mass of the organic material present, it is present throughout the material. So, the total mass due to this process is typically much greater. So, each of this process, whether it is decomposition or disruption or diffusion, it needs on a number of factors. So, what are the factors? That is, one is the activation energy. What is activation energy? Activation energy is a measure of the strength of the surface binding energy. It also depends on the temperature, and it also depends, temperature is again it is a measure of the available thermal energy. So, what is activation energy? So, the activation energy is the minimum amount of energy that is required to activate atoms or molecules to a condition which they can undergo some chemical transformation or physical transport like outgassing. So, each process is characterized by a unique range of activation energies, and that follows different dependencies, like time is also one of the factors on which this outgassing depends. So, we will see those one by one. So, what is the mechanism? So, these three mechanism whatever we discussed, we will tell one by one what is the activation energy needed and what is the time dependence. So, disruption, the activation energy which unit is kilocalories per mole. So, that value is 1 to 10, and the time dependence is, it is inversely proportional to either the time or the square of the time. Then the process diffusion, the activation energy, that is the figure is from 5 to 15, and here it is varies inversely to the square root of the time. And the decomposition, here the activation here the activation energy needed is much more. So, this is 20 to 80, and this does not depend on time. So, the amount of mass loss rate due to diffusion, we can represent it by this relation. We can derive this expression, that is the derivative of the mass, this is a dm by dt, this is the mass loss rate. So, this is equal to you can see this expression where the Q0 is called the reaction constant. So, that is the characteristic of the outgassing property of the material, and which need to be determined experimentally. EA, what is, there is the activation energy which unit is kilocalories per mole, and R is the gas constant whose unit is again kilocalorie Kelvin per mole, and T is the capital T, it is the temperature in Kelvin. So, if you integrate this equation, this is basically a differential equation. If you integrate this equation, then you can calculate what is the mass loss between a time duration T1 to T2. So, this is the expression which shows. So, I get this. So, this gives the mass loss between time T1 to T2. So, this expression says that the amount of matter or amount of mass that is outgassed by a material is dependent on the material's specific outgassing characteristics. So, specific outgassing characteristics which is represented by the reaction constant Q0. So, depending on the material, different material will have different Q0 values, and if you know the activation energy, then we can calculate what is the mass loss. Okay. So, now the next process comes, that is the molecular contamination. So, we discussed yesterday what is molecular contamination. So, whenever there is an outgassing, so what happens, this outgassed particle, they deposit on a cooler surface molecule by molecule and contaminate that surface. So, that is called the molecular contamination. Now, what is that mechanism? So, here this happens by two methods, that is either is absorption or adsorption. So, what is absorption? Absorption is the process by which the material assimilates into another, means the material, the outgassed material, it can even go to the inside the material. So, it is not subjected to the only to the surface, whereas the adsorption is the addition of the molecule to the only solid surface. So, this is the difference between absorption and adsorption. So, this happens when the outgassed material it travels or it transports to a cooler surface and deposits there. So, this is the two processes by which the molecular contamination happens. And disruption is the process of the that is the of removing the adsorbed or absorbed substances from a solid or liquid. So, In addition to the contaminants on the surface of a material, the gaseous atoms may be dissolved in a bulk medium whose distribution is regulated by diffusion. So, this is also a process that is other than the absorption or desorption. The material can be dissolved in a medium which is regulated by diffusion. So, the atoms or molecules that diffuse and migrate towards the surface in contact with vacuum space, then it will dissolve at a higher temperature when the temperature will increase. So, now let us see how the contaminants, that is the outgassed material, it transports. So, the arrival rate of the contaminants at a given point is dependent on the rate of outgassing from all the potential surfaces. So, it may not be one surface, but it can be multiple surfaces from where the outgassing process can happen, and it depends on the physical, that is the orientation of the geometry. We will see it when we will understand it by through some illustration. So, in general, the arrival rate is the product of the rate at which the mass leaves the source, which can be calculated. Now, from the equation of the amount of outgases and a geometrical view factor, which is simply a measure of the fraction of the matter that leaves the source and impacts a given point of interest. So, this outgassing view factor, this bears a strong resemblance to the view factor or angle factor used in the calculation of radiative heat balance. So, we will use the same concept here, which is used in radiative heat transfer. So, let us consider two surfaces. You can see in this figure, one is dA, that is A1, and the other is. So, these are two elementary surfaces has been considered. So, that is why the dA1 and dA2 has been used, and these are you can see their orientation. So, you can just consider a right angle or a normal to this surface dU1, and then the line connecting to the center of these two surfaces, that is given by r. So, this angle made is theta, and the phi is the angle made in this line connecting the centers of these two surfaces with the normal to the second surface. So, this surface is we will consider it is radiating, and this we will consider this is the collecting surface. Okay. So, let us assume that that surface, that d1, it is radiating heat into space with its intensity is I1. I1 is, that is the watt per meter square. Now, what is the fraction of this heat which will impact the surface d2, which is located at a distance r, and already explained what is the orientation with respect to the radiating surface. So, now the rate at which the energy lifts the surface d1 in the direction dA2. So, that we can find, that is will denoted by the term delta of q1. So, this will be basically, now I1 is the intensity. So, I1 multiplied by, so I1 multiplied by d1, it is the radiation, that is the amount of radiation it is radiated by the surface in, you can assume it is radiated in all directions. So, in the direction of the surface, what is that contribution in the direction of the surface, that component will get multiplying it by the cos theta. So, basically it is the direction, if you can consider a position vector along r. So, if you consider this direction, so what is that energy, it is radiated in this direction. So, this is given by this expression. So, basically it is the component of in the direction of r of the I1 dA1. Okay. So, already we said what is theta and what is phi. Okay. Now, the amount of energy that will be intercepted by the surface d1 to dA2. So, it is dA2, d of A2, that we can find it, but what is this solid angle? What is the solid angle? This surface, it subtends at this point, at the center of this. Okay. So, that solid angle. So, solid angle basically the solid angle multiplied by the radius. So, you can consider a sphere, you can consider this as the center, and you can consider a sphere, and this is an area on that sphere. From that point, whatever this, whatever the solid angle, you can consider a solid angle. So, that will be, what is the solid angle multiplied by r square will give you that area. So, this gives the solid angle. So, this is the area, again we need to multiply it with the phi to have its orientation in the direction of where the radiation it is receiving. So, I am getting cos phi A 2 by r square. So, consequently, the amount of energy that leaves day 1 and it is impinges the A 2, I can write it. So, Q 1 2, that is what is radiated by 1 and it is impinged on d A 2. So, this is the expression. So, basically we are multiplying this with the d omega 2 and I get this expression. Okay. So, now in order to find a total energy if I want to find. So, what we will assume that the d 1 is radiating over the entire hemisphere. So, if I consider the entire hemisphere, we can see that then I can consider this phi angle is the total phi angle will be twice pi. Okay. So, I can show that in that case the area, so area will be 2 pi r square sin theta. This is because what I am considering, I can consider it like that, I can consider this is one quadrant I am just showing. So, this is the angle theta. So, I consider a d theta and then so d A 2 is now the entire this strip. So, now if I integrate over that strip over the hemisphere, then I can show, and that is first I will substitute the d A 2 in this expression, from this to this I will substitute, and then we will if I integrate the theta from 0 to pi by 2, then I will get the what is the total energy radiated by the surface A, and I can calculate this. So, you can do the integration and show this is the by putting phi is equal to twice pi and then integrating sin theta from 0 to pi by 2, we can show this is the expression. Now, we can substitute this I 1 in this expression. So, it will be E 1 by pi. So, I get this is the it is the in terms of, now I am getting this what is the fraction of the energy in terms of the total energy radiated by the surface d 1. So, now we can define a radiative view factor from d 1 to d 2 by this expression. So, it is derived from that earlier expression only. So, this is called the view factor. So, basically this is used in thermal modeling, and what is done actually integrating over this d 1 and d 2, it provides a view factor between the two surfaces. Now, for most of the outgassing calculations, the view factor is needed between two surfaces, because if a surface is not in the field of view of the other surface, there is the very less probability it will be contaminated or the outgassing material will fall on it. So, this again it depends on what is the view factors. So, we will use the same concept and expressions here to know that is the outgassing from a surface to a point that is called the collector, and this simplifies the calculation of view factor. So, we use the same expression, this is a view factor expression, and here what is theta, what is phi, what is r. So, again I will not explain the same theta and phi, but you can see from this figure, this is the same figure, how this geometry is. So, this is r actually. Okay. So, now if you perform the integration and over the area of the outgassing source. So, what we have done, we have considered at a point. So, that is why in this figure, just I will show in this figures, when I consider that is the collecting that is not a surface, but a point. So, then this integration, now it is a two double integration, but it will be only having only one double integration, like we have shown it here. Okay. So, if you do that integration over this is the outgassed surface. So, the arrival rate we can find it out. So, this is the expression. So, this is the arrival rate. So, here why the summation, because we are considering a number of outgas that is surfaces which is responsible for the outgassing, and here the dms by dt is the rate at which the mass leaves the source, and what is that rho as that is gram per centimeter cube, it is the mass density of the contaminant, and we sum it over the all possible sources. So, if the source does not have a direct line of sight to the collecting point of view, its view factor will be or the direct deposition will be 0. So, we will now take a small example that is how we can calculate the view factor. So, before that let me discuss this slide. So, an outgassing source may be an extended surface such as a thermal control panel covered with an outgassing paint, or may be quite localized such as outgassing through a spacecraft vent or from a single electrical component. Contamination may also come from thermal blankets or multilayer insulation. If two or more payloads are carried into orbit on the same launch vehicle, one payload may be degraded by the contamination from the other payload. So, this also can happen. Any material that may outgas is a potential source of contamination. So, it is always necessary for a contaminant source to have a direct line of sight to a sensitive surface in order for the source contamination for the surface. So, this gives a clue that the spacecraft designers, they, if there is some outgassed material, there is a probability of outgassing. So, that the view factor is the structure is designed in such a way, so that the sensitive instruments like camera and all these things, it is out of the field of view of the outgassed surface. So, a source may outgas matter into the intermediate surface, which will dissolve matter into surface of concern. Consequently, reflection or disruptive transfer may also be need to be considered in a comprehensive contamination analysis. Okay. Now, we will take one example. So, the question is like this: estimate the view factor from a circular band of radius 1 centimeter to the point on a solar panel that is nearest to the band. The solar panel is attached to the spacecraft by a 1 meter long boom that is located 50 centimeter below the band. So, if I draw the schematic, it will be so there is a boom and then the so this is so there is a band. So, that band diameter is 1 centimeter and this is 25 centimeter and this length is 1 meter. So, we have to calculate the view factor. So, what are the needed? So, view factor is given by, it is cos theta cos phi then d of a and then divided by pi r square. So, here the point is, we will consider this is the point. So, if I consider this point, so this is the distance 1 meter. So, I can calculate what is this distance. So, I need to calculate this distance and this angle is theta and this will give me the phi. So, I am to calculate the theta and phi. So, I will draw it here again. So, this is the point and this is, so this is 1 meter. So, here this is the point, we have to calculate it. So, this is r. So, this is 0.25 meter, this is 1 meter. Okay. So, this is my theta angle and this is the phi angle. So, I can calculate the cos theta and cos phi. So, cos theta will be equal to, this will be 1 by square root of. So, this r will be square root of this plus this. So, it is 0.25 square plus 1. So, I get 1 by 1.03. So, this is equal to 0.97. Then I similarly can calculate the cos phi. So, cos phi will be equal to 0.25 divided by 1.3, 1.03. So, this gives me equal to 0.24 and d of a in this expression is d of a is pi into 0.01. So, I am converting everything to meter. So, this is square meter. So, then the view factor will be given by 0.97 into 0.24, then 0.0009 0.0314 divided by 3.14. So, this gives me the total value of something like 0.000219. So, with this let us finish it here. So, in this lecture I wanted to tell you about what is the mechanism of the outgassing and what is the mechanism of, that is, the outgassed materials, it is transported and it contaminates another surface, and then how we can quantify that, that is the what is the amount of outgassing, and we used a that is a term, that is the view factor. We derived the an expression for the view factor, and we have seen how to calculate the view factor by taking an example. Thank you very much.